Okay. So, so last time we talked about Bezout's theorem. We started the discussion. So let C1 and C2 be two distinct irreducible curve in P2, where K is an algebraically closed P2K, where K is an algebraically closed field of degree m and n respectively. So C1 say is of degree m and C2 is of degree n. Then the intersection is at least one, and the number of points in the intersection is at least one and at most m times n. And in fact, if you count with multiplicity, then it's exactly right multiplicity, then it is exactly m times n. And here the curve has degree m means it's so a curve in P2 is given by a homogeneous polynomial of by a homogeneous polynomial, and the degree of that homogeneous polynomial is same as the degree of the curve. So that is the definition of degree of C1, and similarly degree of C2. Okay, and since C1 and C2 are irreducible curves, the polynomial which defines C1 and C2 are irreducible polynomials, irreducible homogeneous polynomials. Okay. So, so this is the statement, and today we'll hopefully see a proof of this. So there was a lemma. So we will have to work with two homogeneous polynomial, one of degree m and the other of degree n, and this lemma. The first lemma which we saw proof of last time says that we can assume that these two homogeneous polynomial is monic in Z, for instance. Yeah. So that was so a polynomial is monic in Z. A homogeneous polynomial is monic in Z if and only. So we saw that this happens if and only if zero locus of f does not contain 1, 0, 0, 0, 0, 1, yeah, the point 0, 0, 1 of P2. So we just have to take do some linear change in x, y, and z to make sure this 1, 0, 0 does not belong to zero locus of f or g. Yeah, so does not belong to zero locus of f times g, if you like. Then if you make that linear change of variable for x, y, z, then in the new coordinate system, this f and g will be monic in this new variable in this new z. Yeah, and of course the intersection numbers etc. don't change because we are looking at the same configuration from a different angle, if you like. Yeah. So the intersection numbers don't change. So we can the upshot is we can assume f and g are monic in C. Yeah. So before going to the proof, let's see some examples. Yeah. So so maybe example. So if so we were discussing one line and one circle and a line. In fact, let's just take some. So suppose f is a line. Yeah, C1 is a line. So suppose C1 is a line. So what does that mean? F is a linear polynomial, linear homogeneous polynomial. So f is of the form ax plus by plus cz for some abc, some abc, and maybe we can assume one of them is non-zero. Yeah, so maybe c. So in fact, as we saw, we can always assume it's monic in z. So maybe may assume. So in fact, I should yeah. So may assume C is 1. Yeah. and C is -1, let's say. Okay, so that I can write Z equals X plus Y. So C1 corresponds to Z equals AX plus BY. So in this case, you can, this reduces to what I was saying about polynomials in one variable. Yeah. So now, so this is the curve defined by F, and then G is some monic polynomial. Yeah. So but homogeneous polynomial. So CXYZ is homogeneous of degree n. So m is 1 and n is whatever n is. Yeah. So n could be any positive integer. So in this case, the theorem says that C1 intersection C2, the size of this should be at least 1 and at most n. And in fact, if you count with multiplicity, it should be equal to n. Yeah. So what does C1 intersection C2 mean? So we are looking for simultaneous solution. So it intersects means the point lies on both F, 0 locus of F and 0 locus of Z. Yeah. So we are trying to simultaneously solve F and G. F equals 0 and G equals 0. So that means so we know how to solve such equation. What we do is put Z equals AX we can substitute Z equals AX plus BY and try to solve GXY equals 0. Yeah. So GXY AX plus BY equals 0. So trying so. So X and so if A0, A1, A2 belongs to C1 intersection C2, then A1 comma A0 comma A1, A0 comma A1 is, sorry, I should do homogeneous. Yeah, A0 comma A1. So maybe will pretend homogeneity we'll worry about in a bit, but A0 comma A1 should satisfy this equation. Yeah, and A2 will be just A times A0 plus B times A1. A times A0 plus B times A1. Yeah, so this is what we'll have to do. And then this triple, we'll look at the equivalence class of this triple, and that gives us 1 point. So let's just, so now if you think about it, G was a homogeneous polynomial in X, Y, Z, and I've just replaced A and Z by AX plus BY. So this, let's call this HXY. So HXY is a homogeneous polynomial. Is also homogeneous. Yeah, homogeneous polynomial in X comma Y of degree n again. Yeah, so it again remains degree n. Yeah, because we have just replaced ZY AX plus BY. So wherever Z power n is there, you'll replace it by AX plus BY whole power n, and you can check that each term will have again degree n. Yeah, or you just multiply by lambda and you see that you replace X and Y by lambda X and times lambda Y, and you see that lambda power n comes out. Yeah. So either way, we see that HXY is a homogeneous polynomial in X comma Y of degree n over the field K, where K, remember, is an algebraically closed field. Yeah. So again, like in the like yesterday in the quiz solution, I was telling you, if you have a homogeneous polynomial in two variables um, over an algebraically closed field, then it will split into linear factors. Yeah, because you know you just dehomogenize it and then try to solve it. Okay, and so yeah, so this will factor into, yeah, so this so hxy factors. So you think of it this way, hxy. So maybe it is you dehomogenize it. So you know you think of it as um, so this is so maybe I'll just write it this way. Yeah. So hxy is product of linear factors, homogeneous factors. Yeah. So so what is used here is that as K is algebraically closed. Yeah, so for instance, hxy may be of the form, you know, some polynomial. So you can write it as x power n times h. So h is of degree n. So you can write it as x power n times h 1 y over x. Yeah. So now it is a polynomial in one variable y over x, which you can call it u, and try to solve it for u. Yeah, and so this you can write it as x power n times. So this may not now this polynomial h1 y over x may not be of degree n, but maybe something smaller. Yeah. So anyway, whatever it is, it doesn't matter. Y over x minus, so what if the degree is d, say, so you'll find alpha 1 to y over x minus alpha d. So this may be repeated. Yeah, so if it has repeated roots, then some of these alpha i's might be same. So you'll get this because a degree d polynomial over an algebraically closed field is splits into d roots, and then you multiply it by x power n, and you get x power n minus d, y minus alpha 1 x, and so on, y minus alpha d. So if d is strictly less than n, then you will have some so that will tell you that hxy is divisible by x. If d happens to be equal to n, then of course none of the factors are x. Yeah. So that is how you can write. So now of course you can take x to be so now you have various solutions. So one solution, the various solution is x equals 0 if d is less than n, and otherwise x equals 1, and y equals alpha 1. And so on. Yeah. So the point, and then z is a plus by. Yeah. So maybe I'll just write the points in. So x equals 0 corresponds to 0 here, and then y could be anything, and so maybe we can take it to be 1, and z has to be a combination of these two. So a times x, which is 0, and b times 1, which is b. Yeah, so this corresponds to this point, and then each of these ones will correspond. So this will appear with with multiplicity n minus t, and these alpha is so if all the alpha is so whatever multiplicity this alpha I appears with, that's how they will correspond to, and they will correspond to the point 1 alpha 1 a plus b alpha 1. Yeah. So these are the points. So you can see the endpoints with. So these are alpha I, rather I should put, yeah, I between 1 and d. So as you can see, if you count with right multiplicity, you get exactly endpoints. Yeah. So if one of them is a line, it's sort of easy to solve because one of them is a linear thing. You can substitute and do it. So, so in some sense, you have eliminated z, and then it becomes sort of so it becomes homogeneous in two variables, which is almost like an equation in one variable, and equation in one variable we know how to solve it. Meaning we may not know how to solve it, but we know that there are so many roots and so on. Yeah, so the objective was to effectively reduce it to equation in one variable and then try to solve it. Yeah. So so there is a so if neither of them is linear, then also you can do this trick, which is sort of elimination kind of trick, and that method is called that is called using resultant. What is called resultant? So I'll define it, and we will see how it works out in general. Yeah. So are there any questions? Okay, so let's look at the more general setup now. So I hope this example is clear. Yeah. So this is the this connects. This tells you why one should expect this to happen. So it's almost like reducing to the problem that a degree n polynomial in one variable has n roots counted appropriately. Yeah. Okay. So yeah. So the lemma is let R be a UFD and F and G be non-constant polynomials in RG. Then F and G have a common non-trivial factor if and only if resultant of F comma G is 0 in R. So here F and G are so if F is of degree m and G is of degree n, then with these coefficients, then resultant of Fg you can write it via this m cross n m plus n cross m plus n matrix like this. So the n rows of these A zeros, and the m rows of these B zeros drifting one by one. Okay. And yeah, so I'll give you a proof. The proof I gave in last class had some errors. So let's see the proof. Yeah. So suppose first that f and g has a common factor. Yeah. H. So let f equals u times h and g equals v times h, where u, v, h are in Rz with degree h at least 1. Yeah, so that's what common non-trivial factor means. Yeah. Then if you think about it, if I multiply vf, v times f, then you get uvh, and if I multiply g with u, then also you get uvh. So if you take their difference, you get 0. Yeah. Conversely, if there exists uv in Rg non-zero with degree u less than f and degree v less than degree h, and this identity vf minus ug is 0, then what do we get? Then we get that vf is equal to ug, and since degree of u is less than degree f, f cannot divide. So degree of f is bigger than degree u. Yeah, so f cannot divide u. So some irreducible some irreducible factor of f has to appear in the factorization of g. So So all this, so note, we can talk about everything is product of irreducible. Yeah. So note RZ is a UFD. Since R is a UFD, RZ is also a UFD. So you can do a prime factorization, irreducible factorization of this. So some irreducible factor of f of non-trivial irreducible factor, meaning it has to be a polynomial of degree at least 1, has to divide G, yeah, because I mean f does not divide U, yeah. So so that tells us that f and G has a common factor, yeah. So what we have proved is that f and G have a common factor if and only if there exists UV. So we have proved both that if it has a common factor, then you can find UV and H in RZ such that VF minus UG is 0, and you know, degree of U is less than degree of F, degree of V is less than degree of G. Yeah. So in this construction, and conversely. So what we have proved is that f and G have a common factor if and only if this holds. Yeah, there exists UV in RZ non-zero, where you can write it as a polynomial of degree at most m minus 1. So here C0 could be 0, C0, C1, some of them could be 0, but U itself can't be 0. Yeah. And similarly, D0 could be 0, D1 could be 0. So that it need not be exactly degree m minus 1 and degree n minus 1 respectively, but it can't be bigger degree. Yeah, it has to be at most m minus 1. So such that VF minus UG is 0. Yeah. So far we have proved this statement. Okay. So to say that to prove the theorem, it's enough to show that if this holds, if the second statement is equivalent to saying that the resultant of f comma G is 0. Yeah? So determinant of this big matrix is 0. Matrix, which we will call them. Yeah. So let's try to understand this condition. VF minus UG is 0. Yeah. So we'll build up some equations out of it, and that will give us that that identity. So let's look at V times. So V is D0 Z power n minus 1, D1 Z power n minus 2 up to Dn minus 1. Yeah. And F was A0. Sorry, where was F? F was here. A0 Z power m, A1 Z power m minus 1, AM minus 1 Z plus AM. Yeah. So we are multiplying U times F, V times F and U times G. So the top term will be A0 D0 times Z power m plus n minus 1 in VF, and then degree m plus n minus 2 term will be A0 D1 plus A1 D0 and so on. Yeah. And the final term, the constant term will, so it will keep on becoming bigger, and then small, more number of terms in the middle, and then less number of terms, and eventually the constant term will be AM Dn minus 1, AM times Dn minus 1. That will correspond to the constant. And similarly, UG, U times G, you can write it this way. Yes, B0 C0 times Z power m plus n minus 1. Minus, so these will come with negative sign because U times G is with negative signs. So we get that VF minus UG is 0. Is this, which we know should be 0. Yeah. So that means all the coefficients. So A0 D0 minus B0 C0 should be 0. Yeah, and so on. Yeah. So let's write down those equations. So so this is equal to 0 if and only if A0 D0 minus B0 C0 is 0. So what I'm going to do is think of, so I'll write these equations and then convert it into matrix form. Yeah. So we are trying to find UV which satisfies, we are given FG, we'll try to look for UV of this form. Yeah. So we are trying to solve for these CIs and DIs. Yeah. So these one should think of CIs and DIs as variables, and we are trying to write down equations involving them. Yeah. So there are MCIs and DIs. So we should, if we have m plus n equations, then we can say when it has a solution, non-trivial solution, and so on. Yeah. So so that's what we are doing. So to say that z power m plus n minus 1's coefficient is 0 is same as saying a0 d0 minus b0 c0 is 0. And then we set a0 d1. So a1 d0 plus a0 d1 minus b1 c0 minus b0 c1 is 0, and so on. Yeah. So this from by setting z power m plus n minus 1 coefficient 0, coefficient of 0. Okay, and so on. Yeah. So you yeah. So give me a second. Yeah. Yeah. Sorry about that. Yeah. So so we got this this set of equations. So this is coefficient of z power m plus n minus 2 is 0. Yeah, and so on. So if you continue this way, then you'll get this set of equations. And now we are trying to write this in the matrix form. Yeah. So so unfortunately, the way I have learned matrix multiplication or writing matrix equation is this way. So what we get is the transpose of the resultant matrix. So A0 and bunch of times D0, 0 times D1, and so on. Then B0 times minus C0 is 0. This is how I'll think of. So D0 to Dn minus 1 are variable, minus C0 to minus Cm minus 1 are variable, so that we get the resultant matrix. Yeah. So you can see that. So if you write, if you check this, so I've just written this matrix. Yeah. So so the first column of this matrix will be A1 to AM, A0 to AM. The second column will be 0, A0 to AM, and so on. This will go on till we reach this coefficient of z power m. Yeah, and then the point is AM d minus 1, d minus 1 is automatically 0. Yeah, there is no d minus 1. So whatever the other things are becomes 0. So there won't be any coefficient. So if you want the coefficient of z power m plus 1, then you can't involve d0. Yeah, so technically there should be am plus 1 d0, but am plus 1 is 0. So that that term anyway vanishes. Yeah, so you have a bunch of zeros here. And so this is the matrix. Yeah. So this so the equation becomes this matrix times this should be 0. Yeah. This set of linear equation. Is this clear, guys? So this is how we should think of the equations involving this. So last time I cooked up some equations. The equations were correct, but I mean, the solutions have to be of the form z, z square, z cube, and so on. And I thought maybe one can achieve that kind of solution, but there is no way to guarantee that. Yeah. So, but here this is okay. This will have a non-trivial solution. See, all the variables are all distinct. There is no relation between them. Yeah. So this will have a non-trivial solution if and only if the determinant of m transpose is 0, which is same as saying determinant of m is 0. Yeah. And what does a non-trivial solution precisely means? So if it has a non-trivial solution, that means we can find u non-zero, let's say, or V non-zero. So if we find one of them non-zero, the other has to be non-zero, yeah, because we are over integral domain. So if say U is non-zero, then U times G is non-zero. So V can't be zero, yeah. So once we have a non-trivial solution, that means there exists UV non-zero in RZ with degree U less than M and degree V less than N, such that VF minus UG is zero, yeah. So we have shown that these two are equivalent, and this, remember, was equivalent to saying that, so this we have already, so we began with this. So this is equivalent to saying F and G have a common factor, have a common, sorry, stuck, have a common non-trivial factor. So thankfully, I mean, this equivalence. So in our case, when we are working over when R is a homogeneous polynomial ring in two variable over an algebraically closed field, the resultant happen to be a homogeneous polynomial, yeah, and then you can actually factor it into linear factors. So I mean, the application wise, it doesn't change anything, yeah? Even though the statement was not correct. So now at least we have the right statement and the right proof. Yeah, is this clear, everyone? Any questions on the proof?
The starting coefficients can be zero, right? So you have taken minus n minus 1.
I'm sorry, your voice. Okay. Yeah, but your voice is not coming clearly. Can you just type it? And I'll try to answer it. Maybe you can type your question. Who was this? This was Arithro? Ah, okay, yeah, there's something. Coefficient of z power m minus 1 can be 0, right? Coefficient of z power m minus 1 where? In U and V, yeah? Yeah, so so I did say that. So this U and V are of this form, and C0, for instance, could be 0, yeah? So we don't assert that U has to be a polynomial of degree exactly m minus 1. It can be a polynomial of degree less than m minus 1 as well. Yeah, that's right. So some of these numbers, CIs may be 0, but all of them can't be 0. That is what we are asserting. Any other question? So yeah, no issue. So basically, it's this VF minus UG equals 0 is basically when you translate it into solving for U and V, you get this resultant matrix. Okay. So that was the thing. So there are many ways of defining resultant. Resultant basically, I mean, the primitive form of resultant is to check whether two polynomials have a common root or not. Yeah. So if f and g are polynomials over complex numbers, and you want to check whether they have a common root or not, then one way to do is make out the resultant matrix and check. Yeah. There's a related concept called discriminant, yeah? And which is to figure out whether f has which is used to figure out whether f has a multiple root or not. Yeah? So there's a discriminant of f is basically resultant of f and f prime. Yeah? So remember f prime, so f has a multiple root if and only if f and f prime has a common 0. So that is how people define discriminant, and that's also a useful concept. Okay. So f has a multiple root if the discriminant is 0. Great. So you are familiar with resultant and discriminant, yeah. But when you are working with a more general ring, then one has to be a little more careful about the statement. So good. So it's a very old tool, and people earlier used to use a lot more elimination theory kind of method to solve equation. So resultant is not something new. One can, like determinant, one can define resultant in some sort of axiomatic way as well. Yeah. So meaning if you can factor f as in, so you can write f as product of linear factors in where the factors will, the zeros will be not in R but some algebraic closure of fraction field of R, and then you can define resultant as product of differences of root of f and g. Yeah. And then one can show that this has to lie, using some Galois theory, you can show that this has to lie in R itself. So that will recover the fact that if it has a common 0, then the resultant has to be 0. Okay. A common 0 in algebraic closure of fraction field of R. Okay, so I don't know how much you have seen resultant, but it's a useful tool. So these days, thanks to computers and some new results proved using resultants, etc. There's a renewed interest in resultants, and they are quite useful. So if you can do some computation explicitly, then it's quite good. Yeah, so it's quite helpful. Okay, so let's get to the proof of Bezout's theorem. So half of the proof we had already seen. So I'll do the other half. But I'll go through this first half as well, so that I mean, anyway, repetition will help. So remember, f and g are homogeneous polynomial of degree m and n respectively. Suppose fg have no common irreducible factor. Yeah. So that you know, if it had a common irreducible factor, then C intersection D will be quite big. Yeah, so it will have infinitely many points. So that's why we want to avoid a common irreducible factor. Let C equals 0 set of F and D equals 0 set of G. Then C intersection D is the number of points in C intersection D is at least 1 and at most Mn. Yeah. So this is slightly more general than in the sense that C and D need not be variety. It may have many irreducible components, but it's constrained in the fact that it doesn't give you equality. It's giving you some inequality. Yeah. So but even the equality is true. So C intersection D is equal to Mn if you do the calculation in the correct way. Yeah, so you count each point with right multiplicity, even if C and D are reducible. This is true, but that requires a little more work. So let me just do this weaker version of Bezout's theorem. So maybe some people call this weak version. So maybe I'll write it. Weak Bezout's theorem. So f and g, remember, are by linear change of coordinates, we can assume f and g are of this form. Basically, we are trying to ensure that 0, 0, 1 does not belong to zf and zg. So remember, zf and zg are proper closed subsets of P2. So the union is also proper closed subset. So there exists some point which is not on Z of union ZZ. So we can make sure by linear change of coordinate, we can make sure that that point is 0, 0, 1 in the new set of coordinates. Yeah, and that will ensure that F and G are of this form. Then the claim was resultant of Fg. So of course, since F and G have no common factor, the lemma tells us that resultant of Fg is non-zero. Yeah, is a non-zero polynomial. But last time I said it's a homogeneous polynomial of degree mn, and I didn't give you. I said homework, but maybe I'll do this homework for you. So today I have prepared, so it's so I can tell you why this is homogeneous. Yeah. So all I have to show is, so it's already a non-zero polynomial. All I have to show is that it's homogeneous of degree mn. Yeah. So M is a matrix with entries which are polynomial in xy. Yeah. So you can think of it as matrix with matrix over Rx. M is a matrix with entries in kxy. Yeah. So yeah. So this is okay. So maybe you can think of it as in GL M plus N of kxy, yeah, where k is an algebraically closed field. Okay, k is a field is necessary, is what is needed to prove it's homogeneous. Okay, so now look at, so what do we have to show? We have to show that the determinant of M and the determinant of this matrix M lambda x lambda y, they are different by the factor of lambda power mn. Yeah, so we want to show that determinant of M will be yeah, so GL and GL I don't know, but M is a yeah, so I should just write M n cross n matrix. So I don't know if it is invertible. Yeah, so that's why. M plus n. So to check whether this resultant is a homogeneous polynomial of degree mn, we have to check we have to compare determinant of lambda x lambda m of lambda x lambda y with determinant of m. So let's see what is m of lambda x lambda y. Yeah. So remember, A1 is a homogeneous of degree 1, A2 is homogeneous of degree 2, and so on. Yeah. So we have these, and F and G are homogeneous. So AI is homogeneous of degree I, and BI is homogeneous of degree I. Yeah. So maybe. AI X, AI, and maybe I'll write it in short. Yeah. AI and BI are homogeneous of degree I. Degree I. Okay. So if we replace x by lambda x and y by lambda y, then the lambda will factor out from A1, lambda square will factor out from A2, and lambda power m will factor out from AM. Yeah, and whatever is 0 will remain 0. Yeah, and so on. So we get this matrix where we have these factors, and then what we do is we will multiply the. So see, I was telling you factor out some factor of lambda. So we can't factor out some lambda because the first row has 1 1, so we can't factor anything. In the second, first column, and in the second column we have lambda in A1 constant here, and so on. Yeah, then the rest is 0. Then lambda in B1 constant here. So what we can do is multiply the second row by lambda. Yeah. Then what happens is the factor of lambda you can factor out from first column, second column, they all agree. Yeah. Similarly, third row, you multiply it by lambda square, fourth row by lambda cube, and so on. Till you reach the nth row, you multiply it by lambda power n minus 1. Yeah. So if we do that, and similarly among B's, the second row you multiply by lambda, the third row by lambda square, and so on, and the last row by lambda power m minus 1, which is the mth row among B's. Yeah. So we get this is maybe you can write this matrix. Yeah, so it looks something like this matrix. It looks like it's stuck again. Yeah. So you this is how we will multiply each of these rows. Yeah. And then if we multiply this way, then we can factor out things. Yeah. So from first column we can't factor out anything, but from the second column we can factor out lambda. From the third column we can factor out lambda square. From the fourth column we can factor out lambda cube, and so on. And from the mth column we can factor out lambda power m. Sorry, m plus 1th column we can factor out lambda power m. And then from m plus 2th column we can actually factor out lambda power m plus 1, and so on. And when we reach the last column, m plus nth column, we can factor out lambda power m plus n. Yeah, m plus n minus 1. Yeah. So now so doing this operation, how does that change the determinant? So once we factor out these lambdas, what we'll get is the original matrix mxy. Yeah. So we would have factored out all lambdas. Yeah. So all the lambdas will be missing, and we'll get back the matrix M. Okay. So this calculation tells us that determinant of lambda x times lambda y, if you multiply by these the second row by lambda, third row by lambda square, and so on, we are multiplying the determinant by product of these guys. Yeah. Determinant of lambda x times lambda y, when we multiply by product of these guys, lambda power 1 plus plus 2 plus up to n minus 1, 1 plus 2 plus up to m minus 1, we'll get something from where we can factor out copies of lambda square, and so on. So if you which is in effect dividing by lambda power 1 lambda square up to lambda power m plus n minus 1. So this is m plus n minus 1. Okay. And so once we factor out all these lambdas, we get back mxy. So what we get is the determinant of this times this factor is same as determinant of mxy. Is this clear, everyone? Yeah. So this is just matrix manipulation. Yeah. So we multiply these by lambdas, so that changes the determinant by multiplying by what I have written in numerator, and then we factor out all the lambdas from each of the column, and that in effect divides by lambda power this guy, and what we get is so if we do this operation, we get mxy. Yeah. So we get this determinant mxy. Yeah. So that tells us that so determinant of m lambda x lambda y is basically resultant of fg evaluated at lambda x and lambda y, and determinant of mxy is precisely resultant of fg as a polynomial in xy. Yeah. So this identity is same as this is same as lambda power this product, and this product you can check is so this guy. Maybe I can write this in red. Yeah, so this if you calculate it, so m times m minus 1 will cancel out with this negative, n times n minus 1 will cancel out from this negative term, and what you'll get is basically the mixed terms mn and nm, so with 2 factor, and there is a division by 2, so what you get is this is equal to m times n. Yeah, so you evaluate this numerator and what you get is m times n. Yeah, so that tells you that resultant. So what we got is resultant of f g lambda x lambda y is yeah, so this is this will be negative mn, not mn. Yeah, m times n will be with negative sign. Yeah, so what we get is that there's a resultant of fg lambda x lambda y is lambda power mn. So you multiply by lambda power mn times resultant of fg evaluated at xy. Yeah, so that tells us that a resultant of fg is a homogeneous polynomial of degree mn. Yeah, so that was the claim. Okay, so that that gap which I left is also filled, which I had assigned you as a homework. So now if yeah, so now let's use this. So as we observed that if ax minus by is a factor of resultant fg, yeah. So first of all, it's a homogeneous polynomial in two variables. So we can write it as product of linear factors. And suppose one of the linear factors is of the form ax minus by. Yeah. Then of course a and b both can't be 0. Yeah. It's an actual factor. Yeah. So some a b non-zero. Then if you plug in fba, and so you set x equals b and y equals a, then what you get is fbaz and zbaz has a common 0. Yeah, because if you plug in x equals b and y equals a in this polynomial, then f and g becomes polynomial with coefficients in complex in the field K, and of course K is algebraically closed, and then if you can calculate the resultant, then the resultant will be 0. Yeah, because if you plug in the resultant x equals b and y equals a, then this factor ax minus by will vanish. Yeah. So that tells you that there is a common factor, say z minus c, and every factor, I mean, since we are over an algebraically closed field, the factor has to be you can write it as product of linear factors. So it will have a linear factor, let's say z minus c. Then BAC, this triple will belong to C intersection. Yeah. So that proves that C intersection D is greater or equal 1. Yeah. So this is where we sort of ended last time. Now we want to argue that that the number of points in C intersection D is at most mn. Yeah. So so you see, the point is, if we can ensure that so suppose there are mn plus 1 points. Yeah. So if we can ensure that all these mn plus 1 points have different x and y coordinate, then that will give a contradiction, because then resultant will have more than mn plus 1 factors. So we will try to ensure that. Yeah. So we will make some linear change of coordinates so that all the points of these mn plus 1 points have different x and y coordinates. Yeah. So that can be done because there are only finitely many points. Yeah. So let's do that. Yeah. So suppose there are at least mn plus 1 points in C intersection. Yeah. So maybe I'll draw a picture here. Yeah. So suppose there are these points, so many points in C intersection D. So choose mn plus 1 out of them, any mn plus 1 out of them. Now you can actually let's do it slightly differently. So let me draw C and D as well, so that so say C is something like this, yeah, and D is a curve something like this. Yeah. So there are so many intersection points. which and suppose there are mn plus 1 of them. Yeah. So what you do is take any 2 point, and there is a unique line passing through those points. Yeah, even in the projective plane, given any 2 points, you can find a unique line passing through them. Yeah. So you draw these lines, any set of 2 points. So so mn plus 1 choose 2 lines will be there. Yeah, but some finite number of lines will be there. Yeah. So now what we want to do is we want to ensure that none of these lines pass through 0, 0, 1. Yeah, and this we can ensure, right? What we'll do is so of course this is some complicated looking picture, but it's still some curves. Yeah. So of course there exists a point which does not in P2 which does not lie on any of these curves, union of these curves. Yeah. So we'll send that including 0 locus of f and z. So we'll make by linear change of variable we can make that point 0, 0, 1. So we can ensure that 0, 0, 1 is not on any line joining any 2 points to any 2 of these mn plus 1 points. By changing coordinates linearly. Yeah, and in the new coordinates again f and g will look like a monic polynomial. So all this theory goes through. The residue resultant of fg is going to be a homogeneous polynomial of degree mn. Yeah, but now what will happen? So now if in the new coordinates, my claim is that x and y coordinates of any 2 points are going to be different. Yeah, so let's see that. Yeah. So let ABC be a point in C intersection D. Then what do we have? Then so if ABC is a point in C intersection is a point in C intersection D, then the point then BX minus AY is a factor of resultant FG. Yeah, because you know, if you plug in x equals B and y equals A, sorry, x equals A and y equals B, then in this equation, in this new equation, then we see that it has a common 0. Yeah. So resultant, since it's a bunch of linear factors, this Bx minus Ay is a factor of resultant Fg. And suppose there are 2 points with the same xy coordinates. So ABC and ABC prime. They are both in C intersection D with C different from C prime. Then both this point lie on the line Bx minus Ay. Yeah. So so both this line. Both this point lie in Bx minus Ay, which is a line in P2, but this line also passes through 0, 0, 1. Yeah, because you know, plug in x equals 0, y equals 0, and z equals 1. So it passes through 0, 0, 1. So it contradicts our hypothesis that the mn plus 1 points we have chosen. So we have ensured that 0, 0, 1 does not lie on any line passing through any of these 2 mn plus 1 points. Yeah. So that so we can't have this kind of thing that ABC and ABC prime both lie in C intersection. Yeah, with respect to this new coordinates. Okay. So what this says that hence residue Fg has mn plus 1 distinct factors. So if there are mn plus 1 points, then and each corresponding to each point will have Bx minus Ay as a factor of resultant of Fg. Yeah. So we'll have mn plus 1 distinct linear factors, contradicting the fact that resultant is homogeneous of degree mn. Yeah. So it can't have more than mn distinct factors. Yeah, so that that completes the proof that there can be more than mn points. Okay, so I hope this this makes sense. So, but if there is some confusion, you can ask me questions. Yeah, and I hope I can clarify. So there is a bit of a geometric argument. That's why I'm suggesting if something is not clear, you can ask me. Any questions? Okay, so if there are no questions, then yeah, so that completes the proof of this Bezout's theorem. So last time I told you I'll talk about multiplicity at a point as well. Okay, and define multiplicity. So maybe in the remaining 5 minutes, I'll try to motivate the definition. So I gave you roughly what the definition of multiplicity should be. So I'll define this for you here. Yeah. So but I'll define it using some examples so that I mean it makes sense. Yeah. So consider this. So multiplicity of a point of intersection multiplicity of a point is sort of a local concept. Yeah. So we don't have to look at the whole projective picture. We can look at in the affine system itself. Yeah. So consider this. So in kxy, consider two equations. Yeah. So maybe x square plus y square equals 1, and so that gives you a circle. Yeah, and then maybe one intersection is you just take y equals 0, so intersection with the x-axis. Yeah, so this intersection multiplicity should be 1. Yeah, it's sort of from the picture it looks like the multiplicity should be 1, and then y equals 1. So y equals 1, then the multiplicity should be, you know, is sort of intersecting with higher multiplicity, so that should be 2. Yeah. So let's look at this point, yeah, in the picture. Yeah. So what is this point? This point is so this is origin. So here x, or maybe this point, x equals 1 and y equals 0. Yeah. So so that point. So we look at so we look at this local ring around at that point. Yeah. So that is just localizing. So that's same as saying you localize at x minus 1 y. Yeah. And then in this local ring, we want to look at how this point behaves in the in this picture. Yeah. So to get this picture, so if I look at this, I'm looking at this point in the affine plane. Yeah. But I want to look at this point in this as an intersection of these two curves. So as a point in this algebraic set. So to get that algebraic set, I'll have to mod out by these equations. You go mod these equations, so x square plus y square minus 1, and you go mod y equals 0. Yeah. So this is what we get. Yeah. So now let's try to analyze how this ring looks like. Yeah. So y is 0, so you can sort of forget about y. So this is isomorphic to kx, and x minus 1, localized at x minus stuck again. So it's localized at x minus 1, and then you go mod, so y is 0, so you can forget about that, and you plug in y equals 0, and you get x square minus 1, so which is same as x minus 1 times x plus 1. But what do we know about x plus 1 in this ring, in the numerator, in the top ring? Kx localized at x minus 1. What do we know about x plus 1? What kind of element is this? Are you guys with me? Or what can we say about the ideal generated by this?
That is a trivial ideal.
Yeah, so so x plus 1, do you see that x plus 1 is a unit?
That is the whole, right?
Yeah, so this is actually a maximal ideal generated by x. See, the point is x plus 1 does not belong to x, the ideal generated by x minus 1. Yeah, so x plus 1 is a unit in this localized string. Yeah, so we can so the ideal generated by x minus 1 times x plus 1 is same as the ideal generated by x minus 1. Yeah, so this is isomorphic to kx localized at x minus 1 mod the ideal generated by x minus 1. Yeah. But the ideal generated by x minus 1 in this ring is the maximal ideal. Yeah, so this is isomorphic to k. Yeah. So we see that the dimension of this ring over k is same as same as dimension of k over k, which is 1. Yeah. So so what you have to do is basically taking quotient and localization commute. Yeah. So this you can also think of it as dimension of over k of kxy modulo x square plus y square minus 1 y localized at x bar minus 1 comma y bar. Yeah, where x bar and y bar are images of x and y in this quotient ring, in this quotient ring. Okay, so this is the intersection multiplicity. So this you can call as the intersection multiplicity of the point x minus point defined by these two. Yeah, so point intersection multiplicity of the point 1 comma 0 of c comma d, where c is given by x square plus y square minus 1 and d is given by y. Yeah. Similar. So we wanted it to we expected it to be 1. We got 1. Similarly, we will do this calculation little more rapidly here. So here for the other point. So for this point, x is 0 and y is 1. So this is 0, 1. So we are looking at the same curve, but now same two curves, but now we have to prove x equals 0 and y equals 1. So in the neighborhood of x equals 0 and y equals 1. So the ring we are looking at is k xy mod x square plus y square minus 1 comma x. Sorry, y minus 1. So the other equation is this line is not y equals 0, y equals 1. Yeah, so y minus 1. And the point we are interested in, so we are going to localize it at x comma y equals 1, so y minus 1. Yeah, and again so let's just try to look at what happens. So yeah, so y minus 1, so y is equal to 1, yeah, in this equation. Yeah, so we just plug in that and we see what happens. Yeah, so this ring becomes, so maybe I'll just localize first and then quotient out, then it's slightly simpler to write xy mod x comma y minus 1. And so y is equal to 1, so I can forget about this, and you set y equals 1. So basically you give a map from this and you'll see that so y minus 1 is in the kernel, so it's okay. And you have to go mod this equation x square, and if you plug in y equals 1, y square minus 1 is 0. Yeah, so you get this, which is basically kx mod x square. Yeah, so this is isomorphic to kx. So localizing doesn't change anything here. Yeah, so this is actually isomorphic to kx mod x square. Okay, this itself is local. The ideal generated by x is the maximal ideal. Yeah, so anything, so this has only those kind of elements. So further localizing doesn't change anything. It has elements of the form all constants and constants plus x. So whatever is constant plus x, if the constant is non-zero, is already invertible. And so you can check that these two are isomorphic. Yeah, and this is dimension 2 over k. Okay, so these two examples suggest that this definition is okay. Yeah, so let P belong to C intersection D, where C and D have no common component. Which is same as saying that if C is defined by F, if C is Z of F and D is Z of Z, then F and G have no common irreducible factor. Yeah, have no common factor. Then intersection at P of C intersection D is you know, so you can think of C and D as affine curves, yeah, because sort of the definition, I mean, you can always throw, so you are only worried about at a point, so you can always remove some line at infinity and get to that point. Yeah, so this is C kxy mod fg, and you localize at that point. Yeah, so maybe a coordinate tree of way of writing it is you look at the coordinate ring of A2 at P. Yeah, so and look at the ring of regular functions, so which are regular at P. Yes, ring of so set of rational functions which are regular at P, and go mod Fg, and you look at the dimension of this over K. So this is intersection multiplicity of P in C intersection D. So you can also check that if the point does not belong to C intersection D, then this number is going to be, it does not belong to C or yes, does not belong to C intersection D, then this number is going to be 0. Okay. So then what you'll get is this ideal generated by F and G is the whole ring itself. Okay, so maybe this is where I'll stop today, and in the next class we will. So there are other ways of proving Bezout's theorem. So I had one more method prepared, but maybe maybe I'll say something about that method as well. Yeah, next class, and see what else we can. Okay. So let me.